All right. Hi, everyone. So my name's Tessa, for those of you I haven't met yet. I'm currently in this very weird superposition between Oxford and Queen Mary. I packed up my desk at Oxford about a week ago, and I started at Queen Mary in January, so I don't really know where I am right now. And as David said earlier, it's really lovely to have a chance to escape the grim British winter and come here to sunny Sao Paulo, so thank you for that. So today I am going to be talking about what I call the gravitational landscape. And what I mean by this is this space of models for dark energy or for modified gravity, so an extension to Einstein's theory of general relativity that exists in the literature. A lot of these models are motivated, at least initially, as attempts to explain cosmic acceleration beyond a cosmological constant, but certainly not all of them. Some of them are kind of born of high energy physics considerations. There are some unified dark sector models in there, so things that try to explain dark matter and dark energy, and various other things. And even if you are not that interested in going beyond a cosmological constant, even if you're happy with lambda, you should remember that with the next generation of surveys, we are going to push our cosmological model, including GR, into a regime that has not yet been tested. So when you do that, when you extrapolate your model to a new regime, you have to test it is working. So we have to test GR and some sensible alternatives in any case. In particular, I'm going to talk about how we are going to test this model landscape with LSST. And I'll do that in 4 stages. So first of all, we'll do the kind of official LSST bit, and I'll tell you what the priorities for testing this model space with LSST are. Then I'll explain why we've come to that set of priorities. And to do that, I need to say a bit about something called parameterized methods for testing gravity. And I need to tell you about some very rapid theoretical developments that have happened in gravity theory, or MG theory, modified gravity theory, over literally the past 18 months. So there's some very fresh results in here, and therefore my disclaimer is like, I can't guarantee that things won't change in time, but this is the state of the field right now. And finally, if there's time, I'll show you what the current constraints on these priorities are, so you know the baseline we are starting from. Okay, so let's start with the official collaboration hat on. Like probably quite a few people here, I belong to the Theory and Joint Probes group, TJP, of LSST. And within that group, we have a task force that is called the Beyond W CDM group. And this is the set of people who are trying to think about how to test ideas related to dark energy and gravity beyond a simple equation of state analysis. It's kind of assumed that a bound on W, the dark energy equation of state, is going to be made as part of the core kind of cosmological parameters analysis. And we're thinking about what can we do that is richer and more informative than that. I've got on the slide here a snapshot of a document we're just kind of finishing off about now. It's going to be put on the archive, hopefully in January, as an LSST desk note. And in this document, we basically lay out and explain the things that we have decided that should be prioritized for LSST tests of gravity. And to reach this set of priorities, what we did was we looked at this whole landscape of models, and we tried to score them against a set of criteria. Okay, so there's a lot of text on this slide, so please don't try and read it all. You just need to look at the top line here, which are the 5 categories we are trying to score models against. Okay, and we ranked them 1 to 5, where 1 is the best and 5 is the worst. Okay, so first of all, the physical motivation of a theory. Is there some nice kind of fundamental physics story we can tell about why these kinds of modifications should exist? Viability and consistency. So a lot of these extended gravity theories have a property that if you push them into a certain regime of their parameter space, or you push them into a very sort of extreme regime in the setting you consider them, they have pathologies. So they have things that blow up to infinity or other nasty properties. So we favor models that don't have that kind of behavior. Obviously, that kind of behavior is assumed to be a kind of weakness of our understanding that would be rectified in some kind of better developed version of the theory. Thirdly, maturity and calculability. So some of these models have been picked up and implemented in n-body simulations and Einstein-Boltzmann solver codes. Others aren't. Others are really at the level of people just doing analytic work. So clearly, the more infrastructure a theory has in terms of codes already, the easier it is for us to test because we have to do less work to use it. Information content. So does the theory make some concrete predictions for deviations from lambda CDM that cannot be taken away by tuning down a parameter, for example? And finally, accessibility to LSST. Okay, there's loads of really cool work going on strong field gravity. Clearly, those kinds of things are only testable by compact objects. So we're not going to prioritize those theories. We want to prioritize things that we can actually make headline results on with a galaxy survey. Okay, so after considering and ranking our models, what we came up with was a kind of 2-tier system. Yep.
One question, I'm just wondering, do you have an example of a model where you can do full nonlinear n-body calculation and where you can actually calculate and you still can't calculate anything? Like what would prevent you? I mean, if you have equations to do the full nonlinear thing, what is it that you can't? Do you have an example?
Yes. Okay. So there's something called Galilean gravity. I won't talk about it today, really. It seems to have a problem that was first found in n-body simulations. When you put it into voids, into underdense regions, depending on the kind of parameters of the theory, etc., it can, what actually happens is the solutions become imaginary. So for the purposes of an n-body simulation, everything stops, right? It breaks down, you can't go any further. So that's something which is implemented fully non-linearly, but seems to have calculational problems. And it's maybe that theorists need to work more on that model to understand what's gone wrong in that set of equations.
Full nonlinear n-body, it doesn't mean full nonlinear n-body works completely.
That's one example. Okay, I didn't write this table exactly, so I'm not quite sure what the person writing this had in mind, but that's one example. Okay. Right, so as I was saying, so we came up with kind of 2 tiers of recommendations. So our top tier, which note only achieved rank 2, we couldn't find something that we really thought was like a rank 1 prime candidate. But our top recommendation is something called Horn-Deskey gravity. And I will spend a fair bit of time today telling you what Horn-Deskey is and why it made it to the top. Below that, we have a kind of second tier of models, which we feel are worthy of consideration, but should not be prioritized immediately. So we're going to start with working on Horn-Deskey. If later in time there is more manpower, more capacity for LSST tests of gravity, we might start looking at these. So let me say briefly what these other 3 are, and then we'll talk about Horn-Deskey. So first of all, F of R gravity has been around for a long time. It is the simple idea that the action for gravity, instead of just being the Ricci scalar, which is R, is instead some more general function of R. And if you like, GR is just the first term in the expansion of that function. So it's a really old idea. It's very mature. We know a lot about this theory. It has been implemented in embodied codes. The downside is that it's been very well tested, and there doesn't seem to be much interesting parts of parameter space left. Okay, it's not looking like a good, viable alternative to lambda CDM. It made it here because it is a useful kind of benchmark to compare other theories against, because we know so much about it. Non-local gravity is a much newer idea with some very cool motivations. So what's non-local mean? Non-local means that there are terms in your gravitational action which look like 1 over box, let's say, i.e. 1 over derivatives acting on some geometrical object. Let's just put the Ricci scalar in there for now. Okay, and the statement is that this kind of correction to GR could be obtained from a quantum gravity background. So the idea is that you have some quantum gravity theory that gives you your microscopic description of space-time. And the claim is that when you average that kind of thing over a macroscopic region to do classical physics, this is the kind of correction that can occur. Now, obviously, we don't have a theory of quantum gravity, so that's not a proven statement, but there are arguments in that direction. So it's really interesting, but on, slightly unproven ground, and at the moment it only exists in the form of background and linear calculations. There is an embodied code underway, but it's not publicly available yet. And finally, bigravity is this idea that you could have a second tensor field in the universe that couples to your metric. Okay, so you've got the space-time metric of GR, and you have this thing that is almost like a second metric interacting with it. And this theory was really popular a couple of years ago. The downside is that only a short time ago it was discovered to have some of these pathology issues that I spoke about earlier. And so it's kind of on the back burner. Maybe in time theorists will work out how to avoid those pathologies, but right now we don't know how to do that. Okay, so these are our tier 2 recommendations. So let's talk about the top spot, Horn-Deskey, what it is and why it's up there. And in order to do that, I actually need to take a sidestep and talk about something else for a moment. Okay, and I'm going to talk about parameterized methods for testing gravity. So if I had given this talk 5 years ago, I probably would have shown you this slide. And I know some of you have seen this already, so apologies to those people. This is a map I made about 5 years ago to try and represent visually this landscape of gravity theories. Okay, and you can see that it's a mess. And I meant it to look like a mess because that's kind of accurate. And what I've tried to do here in the red text is I've tried to classify theories into some kind of sensible family groups according to their properties. Clearly, it's not feasible to go around and constrain and work on each of these theories individually in our analysis pipelines. So this problem of testing this landscape led to a set of smarter tools. And the idea is to come up with a parameterized framework, that is, some set of equations with some free parameters or maybe some free functions in them, some kind of freedom, onto which you can map all of these hundreds of gravity models. So it's a bit like building yourself a machine with a set of dials, and by twisting and turning those dials to different settings, you can recover the properties of any individual theory. And if you can do that, if you can build that, then you can just focus on constraining those parameters or those freedoms. And anyone who comes along later and cares about a particular model in here can reverse the mapping and work out what your constraints mean for their theory. So it's a very nice sort of agnostic way of phrasing your constraints that protects you from the rapidly kind of shifting fashions of gravity theory. So this idea has really taken off. I think CFHT Lens were the first collaboration to really publish results with it. Kids, Planck, very recently, Des Y1 extensions paper, all used parameterized methods, and so it seems very natural that LSST should do the same. And the tricky part here is actually building that parameterization, because you have to make it as general as possible, so it encompasses as many models as you can, whilst keeping it as simple as possible. So you want to keep the number of parameters to a minimum so as to not dilute your constraining power. And a bit more technically, make it as accurate as possible. It has to be a good representation of the models it's trying to capture. Okay, and this is the challenge. So let me tell you about the kind of simplest thing you might try and do, and then I'll tell you about the kind of next level improvement on that. So the simplest thing you might do is to look at these two equations, which come from linear perturbation theory in GR. Right, you've got the Poisson equation, which relates gravitational potential to density fluctuation delta, and you've got a kind of equivalent expression for your lensing potential, which, remember, is the sum of these two objects that appear in the conformal Newtonian gauge, etc., etc. Again, related to your density fluctuation. And the simplest thing you could do would be to look at this and say, this is GR, so I'm just going to fudge in two factors to quantify deviations from GR. And I'm going to write them as 1 plus stuff, where here we'll call the stuff mu, and here we'll call the stuff sigma. And we have to make them functions of redshift in order to be consistent. Okay, and then what you want to do, of course, is to work through your calculations of observables with these modified equations and get constraints from your data on mu and on sigma. And this is exactly what happened in the Des Y1 extensions paper. There may be some people in the room who were involved in this, so I will kind of defer any questions to them. I'm not a member of DES. But they produced this nice plot showing constraints on the values of mu and sigma at redshift 0. Okay, and the DES data is here in blue. Because it's Y1 and it's mainly lensing, it's principally constraining sigma, and so they combine with external data sets to get this much tighter set of contours which are centered on the GR value. Well, centered, they are encompassing the GR value easily at 0.
What's the external data?
I forget. Anyone who's on DES want to tell me what the external data was? I think it was things like Planck and BAO and supernova, all the usual suspects. Yeah. Okay. So this is a really nice, simple way to get a kind of basic litmus test. Is it GR or not GR? And that's a good first step. The problem with that is that it's not super informative for shaping the future of gravity theory. Okay, so it doesn't tell me, for example, which kinds of gravity theories in my big messy diagram are working well and kind of give predictions that are consistent with the data, and which kinds of theories are giving really wacky predictions and I should stop working on them because they're ruled out. So it's not really giving me much guidance for the future. So that's why there is work on developing more advanced versions of this parameterized idea. And that is what I'm going to tell you about now. So the kind of next level version of this, you might be able to guess, goes by the name of Horn-Deskey gravity. Okay, and this is the thing that was in the top tier of our recommendations. So what is Horn-Deskey gravity? In words, Horn-Deskey gravity is the most general theory you can write down that has a metric, just like general relativity does, and has one extra scalar field that is coupled to that metric and changes the properties of gravity in an interesting way. And that's the kind of basic features that underlie a lot of models in that landscape I showed you. Now note that I said it's the most general theory. What that means is Horn-Deskey gravity is a parameterization. It contains some freedoms, and I'll show you in that in just a moment. So you should think of this like a parent theory, and it has many offspring theory that belong to it. There's one restriction, which is that Horn-Deskey gravity only gives you equations that have second-order derivatives in them. Okay, and that's basically to avoid bad stuff. You can show that if you have higher-order time derivatives in your equations, generally it leads to pathologies and nasty things. So we'll kind of just ignore those theories. I'll show you Horn-Deskey in more detail on the next slide. I need to tell you just about 2 bits of terminology that often kind of float around Horn-Deskey gravity. So Horn-Deskey gravity was put out there and shown to be the most general thing, et cetera, and then a couple of years later, a team in Paris kind of figured out that there was a clever way to find some terms that had been left out of the original Horn-Deskey framework. And so this led to the imaginatively titled Beyond Horn-Deskey, which is basically Horn-Deskey plus some extra terms that should be there. Unfortunately, this method was then further generalized to find yet more terms, and this gave birth to an even more complicated theory called DOST, which stands for Derivative Higher Order Scalar Tensor Theory. The good news is you don't have to worry about DOST. DOST is mainly a plaything for theorists. If you actually try and do cosmology with it, so you put it on an FRW background, it basically just reduces to beyond Horn-Deskey. Okay, so don't get misled into thinking this is kind of some separate theory. For most purposes, and certainly for today, you only need to know about Horn-Deskey and this kind of beyond Horn-Deskey extension. Okay. Right, yeah. So this is a theory talk, and so I can't really tell you about Horn-Deskey gravity without showing you the action. So I will do that, but I'll try and do it slowly and piece by piece, and hopefully manage to explain what everything means. If it's not clear, please stop me and ask. So this statement basically just says that the action for Horn-Deskey gravity is going to be a sum of 4 Lagrangians coupled to some standard matter content that we won't worry about. I've never understood why this starts at 2 instead of 1. So there are 4 Lagrangians, L1 clearly got dropped. So there are 4 Lagrangians, and you add them together to get Horn-Deskey gravity. So L2 is the first one. You should think of this as like the generalized version of a kinetic term for your scalar field. And rather confusingly, L2 is not a number, but a function we will call G2. And G2 is going to be a function of the scalar field, phi, and what we call X, which is basically just the kinetic term of the scalar field. So it's phi dot squared, roughly. Added to that is something called the cubic term. Cubic term is, again, another function, G3, again, a function of phi and X, this time multiplying box phi. Okay, so you can see straight away there are these functions in the action that I'm not specifying because Horn-Deskey is a parameterization. These are the freedoms of the action that you tune to recover all those different models. After that, things start getting a little bit stickier. L4, the quartic term, contains another function, surprisingly, called G4, which appears multiplying the Ricci scalar, and then appears with a derivative taken. So G4 comma x is the derivative of this function G4 with respect to this argument x, multiplying some stuff we don't really care about. And the quartic term is important because it contains the GR limit, right? Note that I could recover GR from this action by setting G2 to 0, G3 to 0, and setting G4 to be the Planck mass. Okay, so GR lives in there. And finally, there is one more term which contains one more function, which is the quintic term, contains this function G5. Again, it appears once on its own and once with a derivative taken, multiplying a load of muck. Right, and all this looks messy, but a lot of this mess is actually what gives the theory interesting properties in that it allows it to change the behavior of gravity whilst still screening, which is a term some of you may have heard of. Screening is basically a way, which I won't discuss today, that allows these theories to be consistent with solar system constraints and galactic constraints on gravity. So it basically hides all these modified gravity effects in certain environments. Okay, so I know this looks like a bit of a mess. I've tried to help you out with the coloring here. All you really need to focus on is these 4 functions, G2, G3, G4, and G5. Okay, so those, as I said, are the descriptors of Horn-Deskey gravity. They are what you map theories onto, is a specification of those functions. I mentioned there was this extension called beyond Horn-Deskey. All you really need to know is that it adds 2 more of those G functions. Now, here is where life gets a little bit awkward. What we usually do is that we take this set of G functions and we map them onto another set of functions we call the alphas. Okay, why on earth are we doing that? So what I just wrote down is the kind of full theory action for Horn-Deskey gravity. And what you want to do is calculate predictions from that. So you take that action and you start varying it and you start working out, let's say, the linearized field equations. And you take those field equations and you calculate observables. By the time you get to calculating something like a matter power spectrum or a weak lensing power spectrum, the modification to GR is a big mess of G's, right? And if I went and said to someone, you know, constrain this kind of complicated mess of G's, it would be a really difficult thing to do. So what we usually do is we redefine this set of functions in the linearized field equations. So we take the messes that appear in the field equations and we lump them together and we say there's another 4 functions here called the alphas. Okay, and the point is that this set of alpha functions are much closer, okay, I'm a theorist, from my perspective, much closer to the observables than those G's were. So that means that theorists can go happily do their thing and work on the G functions. From an observational point of view, you're much better off trying to constrain these alpha functions. And all you need to know really is that there is a straightforward mapping between the two. And you only need to touch that mapping in a few cases. So what we put forward as what LSST should actually constrain are these alpha functions. And so there are still 4 of them. They're called alpha K, alpha B, alpha M, and alpha T. And I'll tell you why in just a moment. And they're functions of redshift.
Sorry, why they're not functions of scale?
Because note that the Horn-Deskey G's were not functions of scale either, right? So the scale dependence is actually already taken out in the Horn-Deskey action, which is different to mu and sigma, which might be what you're thinking of. Okay, so these are the things we actually want to work with. I know it seems a bit kind of excessive, I need to tell you about both because of the theory results I want to tell you about in a moment will both involve alphas and Gs. Again, the Beyond Horn-Deskey extension basically just adds one more parameter to the set. I know there are two up here, but by the time you take the field equations, they just merge into one, which is called alpha H. Okay, and you should think of these alpha functions as the kind of compromise between these very theoretical things that appear in the action and the mu and sigma parameterization that I said was a bit too phenomenological to be super useful. Okay, so why do they have these names? The nice thing about these alpha functions is that there are words you can kind of drape around them which tell you what they do, what they mean. So alpha T is T for tensor. Okay, it's the tensor excess parameter. And what it does is it controls the speed of gravitational waves. So very often in your modified gravity theories, your speed of gravitational wave propagation can be different from the speed of light. So we write it as ct squared equals to 1, the speed of light, plus this quantity alpha. And in principle, alpha can be positive or negative. There are now constraints on alpha, which I will discuss shortly. Alpha k is the kineticity parameter. It tells you whether your scalar field has a kind of standard kinetic term or some very funky, exotic kinetic term. Alpha b is the braiding parameter. It tells you about the interaction of your scalar field and your metric. Alpha m is a really important one. It is the run rate of the Planck mass. So a lot of these gravity theories can give you what looks like an effective time-evolving strength of gravity, i.e. a time-evolving Planck mass. Alpha m basically quantifies that run rate, where m squared here is the effective Planck mass. Finally, there's alpha h, which was the one that came from the Beyond Horn-Deskey extension. We won't really focus on that today. It's a bit more technical. The jargon is that it quantifies distal symmetry properties of your theory. So these 5 parameters, but mainly the first 4, are what we want to get a handle on. Now, the problem here is that what I've put forward for constraining is a 4 or 5 dimensional functional parameter space. Okay, so these are not constant numbers, they are functions of redshift. So that is a big ask to constrain that, right? There's a lot of freedom there. And so what we really want to do is try and get as much prior information on these parameters before we go and actually constrain them. Okay, so what I'm going to do now is tell you about 3 recent developments which help to give us that prior information. Okay, they try and whittle down this kind of big open parameter space. And interestingly, all 3 of these developments have been sparked by the discovery of gravitational waves, or the direct detection of gravitational waves. So this is all very recent. The first one, you probably, yes?
These alpha parameters, they are related to just one function or a combination of functions?
Right, I will show you an example in just a moment. They are related to combinations of the Gs. So basically, alpha equals linear algebra expression of Gs and derivatives of Gs. Yeah. You'll see it in a moment. Yes.
So all these alphas, are they the same as just in the EFT approach?
Right, so you mean the EFT of dark energy? Yeah, right, so exactly that. So actually the EFT work kind of came slightly earlier and turned out to be a slightly messier route to something which is actually equivalent to Horn-Deskey gravity. Yeah, so for scalar tensor theories, they are equivalent. Where they become not equivalent is if you want to put in other field contents. So you want to consider bigravity or things with vector fields or two scalars, which I won't talk about today. But yeah. Okay, so our first result comes from GW 170817, which probably needs no introduction. I assume everyone heard about the binary neutron star merger that was detected. And what I have here is a grab from one of the original LIGO papers. And in the bottom panel, you can see the frequency chirp. Is that? Oh, no, it's that. Sorry, I could hear it. You can see bottom panel, you've got the frequency chirp of the merger. And in the top three panels, I've got gamma ray spectrographs, integral and Fermi. And you can see that it's actually about 1.7 seconds after the merger, there is this sort of coincident peak in gamma ray flux, which is associated with the merger. So that simple fact from one event that the gravitational waves and the first photons to get out of the merger, which are the gamma rays, arrived at Earth within 2 seconds of one another, actually puts amazingly tight bounds on any difference in speed between gravitational waves and electromagnetic waves. And if you do the numbers, in the most straightforward case, the bound you get is actually that this alpha t parameter must be less than 10 to the minus 15. Okay, so it's an incredibly tight bound. If you want to be a bit more conservative, make less assumptions about what's actually happening at the moment of merger, you can weaken it a little bit to about 10 to the minus 12, but it's still super, super constraining. So unless we got very unlucky, unless something else happens when we collect more events, this seems to be telling us that gravitational waves have to propagate at the speed of light. And therefore, we should strongly disfavor or possibly even discount altogether models that have a difference in those two speeds.
Is there some specific redshift for this bound?
Right, so that's what I was referring to. So of course, this is only one event, and it happens at redshift 0.01, right, for this event. Strictly speaking, it's possible that we go and get our next binary neutron star merger at redshift 0.2 or whatever the reasonable value is, and we found that this was, some local effect, and actually things are doing something very different at a different redshift. It's possible, but kind of unlikely, right? We would have to be very unlucky if that were the case. So I'm going to assume that is not the case, but it's a fair caveat to make. Okay, so what does this actually do then to the Horn-Deskey action I showed? So I said I would show a mapping between the alphas and the G's, right? I haven't derived this, I've just pulled it out my hat for you. But here it is, this alpha t function, some prefactors we don't care about, and it's related to this combination of the G functions. So it just depends on G4 and G5, G2 and G3 don't feature here at all. And the statement I just made is that this thing, we think, should be equal to 0. So the kind of straightforward way to do that is to say that each of these three things that appears in here, these derivatives of G4 and G5, have to be set to 0. You could, again, make an argument for these things kind of being very finely balanced and cancelling each other out. That's quite hard to do as a general function of redshift. So if higher redshift observations give us the same result, then we don't think that's happening. So we're going to assume that each of these things is individually 0 and see what that does to our few slides ago, which was the Horn-Deskey action. Okay, so here it is again. And note that we now know that G4, x is 0. So straight away, that goes. We also know that G5, x is 0. So straight away, all that mess in the last line goes. Now you can actually show that this kind of remaining piece of L5 can't survive on its own. you can basically get rid of it by doing an integration by parts and using a Bianchi identity, and this thing also has to vanish. So what you're left with then, out of that framework we wrote down, is that you are only allowed to have L2, L3, and this kind of stump of L4, where this function G4 can now only depend on phi. It can't depend on x anymore. Okay, so this kind of gives us a much reduced template for what viable theories of gravity, at least those just involving scalar fields, must look like. As some of you in this area will know, this actually ruled out some of the very popular models, such as the quartic and quintic Galileans. Okay, so here's the reduced template we're left with. I've just taken those remaining bits of the action and kind of written them all on one line. So things like f of r gravity do survive because they do map onto this template, right? Here is how you tune this thing to recover f of r gravity. So some models survive, but the more complicated ones seem to be disfavored. So that was our first result. Yeah, okay. So what came next were regards to that beyond Horn-Deskey extension that I told you about. So initially, it seemed like that extended family may kind of harbor more survivors because the extended beyond Horn-Deskey model has some extra parameters, so it's got a bit more freedom to be consistent with the gravitational wave results and yet still do all kinds of exotic things. So we thought we were saved. However, just a few months ago, a team from Paris put out this paper in which they show that in this beyond Horn-Deskey extended family, most theories are unstable to graviton decay. Okay, and what that means is basically your gravitational wave, we usually call it gamma, comes along and will decay quite rapidly into particles of your scalar field, bosons of your scalar field, which we call pi. Okay, so that's really alarming because the fact that gravitational waves are reaching us undecayed away suggests that this can't be happening, right? So that automatically seems to tell you that there is something wrong with beyond Horn-Deskey. It doesn't seem to be, well, it doesn't seem to match reality. So this result is reached via a lot of kind of heavy lifting in quantum field theory, which you'll be relieved to know I'm not going to do. But I will show you one result, which is the decay rate, right? This is a decay rate for your gravitational wave into your scalar field. This is the result. P to the power 7 is just a momentum factor, so don't worry about it. There's a bunch of constants. Lambda star here is just an energy scale. Again, it's not important for our discussion. What you should notice is that there is this bracket on the top, which is 1 minus CS squared. CS squared is the speed of propagation of perturbations in your scalar field. So if CS squared is 1, i.e. the speed of light, which is possible, then this whole decay rate goes to 0, gravitational waves don't decay, and your model survives and becomes a viable, well, at least for these concerns, a viable model of alternative gravity. So there's this kind of little annoying loophole left, right? Most of this beyond Horn-Deskey family is ruled out, but there's this one small island of models that survive, which are those with CS squared equal to 1. How am I doing for time? Okay, so that's result number 2. Quickly, result number 3, the last in this section, came from considering, again, the quantum properties of this reduced template action. So when you build a theory of new physics, you need to check for something called radiative stability. Okay, what's that? This is a bit of jargon from quantum field theory. What you have to do, essentially, is calculate loop corrections to your action. loop corrections are basically quantum fluctuations. So you have to calculate the amplitude, i.e. the likelihood, the probability of quantum fluctuations to your action being large and changing its behavior. Because if your quantum corrections are large, they are basically going to completely dominate over whatever classical prediction you're making from your nice theory. So you want to do these loop calculations, and what you hope to find is that the amplitude of these loop calculations is suppressed by some really large number, like the Planck mass. And that's what's happening in GR, is that the loop calculations are suppressed by the Planck mass. So unless you happen to be doing Planck scale physics, you don't have to worry about them, and you can use GR as a classical and predictive theory. Okay, so this is the kind of basic check that needs to be done for this action. Okay, again, this is a kind of a sort of pretty heavyweight calculation in QFT, and again, I'm just going to show you the result and tell you what it means. First of all, this term here, this was the kind of kinetic type term, is fine. It doesn't cause you any problems. Problems seem to occur from the interaction of these two terms here. So you do this loop calculation, and it involves two numbers. One of them is an energy scale called lambda star. It can be anything below the Planck mass. There are ways of arguing what it is. All you need to know is it's smaller than the Planck mass. And there's a number called V, which is basically a free parameter that counts the number of loops in your Feynman diagrams. And the final result you get to, for the amplitude, the probability of these quantum corrections, looks like this, which I realize is not kind of immediately readable. So let me tell you what it means. This term here is completely normal and standard and what you'd expect for a scalar field. This term here, you can argue, based on this energy scale that's on the denominator, is either small or order unity, so you're not that worried about it. This term here is of order unity. This term here, note that it has Planck mass divided by this energy scale lambda star, which we said was smaller than the Planck mass. And this is raised to some positive power V. So this thing here, unless you are doing Planck scale physics, which we're not, is really big. Okay, and that's a problem because it means this whole loop amplitude business is large. And that means you can't trust this action, essentially. It's radiatively unstable. You can do the calculation again with just one of these two terms switched on. So either just G4 or G3, and you can show that everything is fine. Okay, so the problem seems to happen when you have both of them turned on. And that's a useful bit of information for what I said we want to do in terms of constraining this parameter space. It tells us we should only consider models which have one or the other. As I said, this is very recent work, as in only a couple of months ago. So there are assumptions, there are loopholes, and maybe later on there are counterclaims. But at least for now, that is what the theory community is saying. Okay, so I've told you about three things which all seem to cut out parts of this model space or bound this model space in some way. And as I said, the hope is that this can then shape our analyses and make it tractable. And make it possible to test this theory space completely. So sometimes people think that if you work on modified gravity, it's that you want modified gravity to be true. And I don't agree with that. I'm very objective about this. We build the model space and we test it. And if we test it completely and there's nothing, that's science. Okay, so these results are all helping us to perhaps reach an end game where there is actually a tractable parameter space that we can completely test with LSST. So finally, just in my last few minutes, I will just say a few words about what the current status of constraints on these parameters is. Now, I remember I told you that they were, these alpha parameters were the things you actually wanted to constrain easily with data. And I said they were functions of redshift. And that's going to make your life hard because you have to constrain a function and not a single number. So what we usually do is we plug in an ansatz for the redshift dependence of these functions. And what I've got on the slide here are two common ansatzes that we're using at the moment. So this one says that your parameter, alpha parameter, is proportional to omega lambda, with some constant of proportionality we generally call C. Okay, so that makes life easier, then you just have to constrain that constant of proportionality. An alternative guess is you could put it to be some power law in scale factor. Then you've got to constrain two numbers, which is the proportionality constant and the power law index. Okay, note that this is a bit of guesswork. Up until this point, everything's been very rigorously derived using proper field theory techniques. At this point, we are kind of plugging in guesses to make things workable. Yeah, okay. So these two forms have been adopted and used in constraints. So here is, again, a very recent paper from Nolla and Nicola, who used Planck data, SDSS, BOSS, and 6DF data for matter power spectra, BAO, and redshift space distortions. And they tried to use all of those things to constrain alpha M and alpha B. And they just chose those two because those are the most relevant parameters for structure formation. Okay, you can show that they have the strongest effect. And they used this ansatz here, which means that they are constraining effectively CM and CB. Okay, and what they get is this kind of unusual sort of bullet-shaped contour. And we understand why that is happening. The upper kind of bound here is coming from growth rate data. So if you make this CM parameter very large, you have a very rapidly evolving Planck mass, you basically boost or suppress the growth rate by an unallowable amount. And the bottom contour here is coming from stability criteria. So if you make CM very negative, your theory falls into one of these kind of pathological regions that I told you about. So together, they're giving this kind of unusual shape. Okay, how am I doing for time? Okay, they did also constrain this form here. All you really need to take away from this plot is that trying to constrain these power law indices is really difficult, right? There's basically not a constraint here. So the only well-constrained kind of plot here, again, is on the amplitude parameters. The time dependence seems to be really hard to pin down. Oops. So in numbers, here's what you just saw, just kind of translated into 95% contours, 95% bounds for those two forms of the parameterization. And you can see that it's about order unity at the moment. That is the current status of these parameters. So just to finish off, I have a plot I stole from David, which he made in 2017, showing a forecast for the constraints, again, on CM and CB, using, in the case of the red ellipse here, stage 4 CMB data and both lensing and clustering data from LSST. Now, on this plot, you can see bounds are improved, but perhaps not by a spectacular amount, right? I said previously, current constraints are of order unity, and here they're kind of down by a factor of 2 or 3, but it's not orders of magnitude. David made this plot before any of those 3 theoretical results I told you about had happened. So what I would like to know now, and something that I think needs to be done in the near future, is to get a repeat forecast and understand now with all this kind of new theoretical developments and our much reduced parameter space, how much better can we do? Is it still like this? Is it orders of magnitude better than this? So that's something I think hope to see in the near future. Okay, I'm basically done, so I will just very quickly summarize. What have I done? I have hopefully convinced you that parameterized methods are the way to reframe tests of gravity such that they stay relevant and don't become outdated. I've shown you Horn-Deskey gravity, which is arguably the best sort of way of doing this at the moment. I told you about these 3 theoretical results, which are all sparked by gravitational waves. So gravitational wave astronomy is really influencing dark energy and gravity work. And finally, I showed you current constraints at the order unity level and hopefully to soon improve. Thank you for your attention.
Questions?
Okay, thank you. So let me just see if I understood this correctly. So if the speed of sound of propagation for the scalar sector is 1, then the gravitational decay bound does not apply.
Does not apply. Yeah, that's correct.
And so,
yeah.
But what does CS equals 1 imply for other functions? That they're not function of x or something more?
Right. So I perhaps should have written this on the slide, but I didn't want to bombard you. So CS squared, you can derive from Horn-Deskey gravity, and you can translate it into alphas, and it's basically a combination of alphas. Okay. It's actually, it turns out to be one of these, it's a ratio with like 3 alphas in the numerator and 3 alphas in the denominator. I can show you an expression for it. So what it requires is some kind of, what am I saying? So some kind of conspiracy between your alphas to give a fraction the value 1.
You showed how the measurement of sound speed and speed of light and gravity gave a lot of constraints. What would be your next kind of observational hint from gravitational waves that could help?
Right. Okay. So thank you for asking about this. It gives me a chance to talk about something I'm doing right now. So the other kind of big observable from gravitational waves is their luminosity distance, at least for this kind of purpose. So from the amplitude of a gravitational wave, well, okay, let me start again. If you have a gravitational waveform with an amplitude and a frequency and some evolution, you can, as we know, compare that to template banks, and you can try and get an estimate of the masses and the things involved in that merger. And if you think you know the masses of your binary neutron stars, let's say, in principle, you have an idea of what the amplitude of your gravitational wave then is. And so you can use that then to get a handle on what is called the luminosity distance of your gravitational wave source, in analogy with electromagnetic sources. So you can get a measure of how far away it is. You can show that if there was a modification to gravity of the kinds I've spoken about here, it would affect the luminosity distance of your gravitational waves, but it would not affect the luminosity distance of an electromagnetic counterpart, such as a host galaxy or whatever. So what you would then be looking for is a mismatch in the luminosity distance of those 2 signals with something like GW 1708-17. Now, that particular event was too close by to really be of much use, but for things at higher redshift, that would be my next kind of thing on the hit list.
What question?
Are there studies of the impact of these theories that are still viable on nonlinear regime simulations or something that probes the nonlinear regimes?
Right. Excellent question, and you have hit the nail on the head. And actually, this was something I was talking to Rogerio about earlier. These Horn-Deskey parameters are not yet implemented in simulations. They have been implemented in an Einstein-Boltzmann solver, which is called high class, so you can work out all your nice linear observables from them. No one has yet kind of quite had the guts to put them into a code, because that's a lot of work. And actually, one thing we are really hoping to get started within the Beyond W CDM workforce is exactly that. So if someone out there, works with simulations and is up for implementing that kind of thing, we would love to hear from you. Yeah.
I'm just curious, these remaining Horn-Deskey theories, how do they play with the swampland conjectures that have come out?
How do they play with the what, sorry?
Those swampland conjectures on...
I think I'm going to say not at all. Okay. I mean, so what you're saying is that, okay, I'm not a string theory person, but the string-inspired models that do or do not live in the swampland should ultimately be able to map onto the Horn-Deskey functions and therefore should be subject to the Horn-Deskey constraints. Mm-hmm. I don't know because I have not done that mapping. Okay. But it's a good thought, actually. I don't know.
More questions?
It's a naive question. Can you include models of massive gravity in Horn-Deskey?
Right, okay. So Horn-Deskey gravity was a parameterization that subsumed everything that had one extra scalar field. What you need for massive gravity is something that incorporates extra tensor fields, right? And that does exist. I didn't talk about it today because it gets more complicated, but it's something the Oxford team and I have worked a lot on. So you can generalize everything I've said today to vector fields and second tensor fields. The problem is, in order to do that, you have to have more free functions, so more alphas. This table actually shows you the number of functions in the middle column that you need to encapsulate everything that has this field content. So massive bigravity, 2 metrics, G and Q, needs only 5 functions. So that's not so bad. But things like the vector field theories in the third line need 7. So that's why we prioritize Horn-Deskey first for LSST, because it's the kind of simplest, interesting thing. But in our dream scenario, we would do bigravity as well.
Can you, in some way, relate the propagation, the speed of propagation of gravity waves to the mass of graviton in that direction?
So, okay, I'm struggling to hear you. I think you're saying, what do the speed of gravitational waves imply for bigravity, for the mass of the graviton? Yes. Right. So they do translate into a bound on the mass of the graviton. The astonishing thing is that it's not competitive. So the gravitational wave binary neutron star merger results bound the mass of the graviton to be less than 10 to the minus 22 eV, which seems tiny, except that the mass of the graviton is already bounded to be 10 to the minus 32 eV or less from lunar laser ranging. It's absolutely mind-blowing, this simple act. Do you know lunar laser ranging? We basically send lasers up to the moon. We bounce them off mirrors on the moon and collect the photons back at Earth and measure the round trip time. And because of the round trip time, you can measure the separation of the Earth and the moon very well. And that's, basically you can test for the presence of fifth forces. So you can get a bound on the graviton mass. And it's incredible that such a kind of mucky experiment actually really, yields this incredibly tight bound on the graviton mass. Better than gravitational waves. Yeah.
So I have a question. So you said that gravitational waves play a big role here because, of course, the speed of gravitational wave ruled out a big chunk of
of the parameter space. But will this continue to be the case in the future? Because now that this very loose parameter is measured, what else can you really measure with gravitational waves that cannot elsewhere? So, for instance, do B modes of CMB will tell anything about these theories, or they are just late-time gravity and it's completely irrelevant?
Right, okay. First of all, when I said a lot of this is sparked by gravitational waves, yes, the bound on alpha T, but also more generally, it got people thinking about these issues like graviton decay that hadn't really been developed enough previously. So it's more general than that. B modes of the CMB, probably not likely to do much. The general intuitive assumption we're working on here and was reflected in my parameterizations is that we think modified gravity is a late time phenomenon. Early dark energy models have been considered, if you know Migne Calabrese, early dark energy bounds, they seem to be very tightly constrained. So likely CMB modes are not going to be the tool of choice for us.
So thank you.
All right.
Our last talk today from Rafael Bravo, a generalized no-Gaussian consistence relation for single-field inflation.
Okay, thank you. Thanks to the organizers for giving me the opportunity to speak here. First of all, my apologies because we talk about the early universe, in particular inflation. And this is a workshop about large-scale structure and late-time universe, so sorry for that. Okay, this work is based in these two papers, which have been in collaboration with these people from Chile and this guy from the Netherlands. I think it's an interesting result that I hope that it could be tested with future galaxy surveys. Okay. This is the part of my talk. First of all, I will give you more than a motivation and an excuse of why I will talk about this subject here. Then I will introduce the ingredients that I will use along the presentation. Then I want to show you a model which violates the well-known Maldacena consistency relation. And then I will show you how we can generalize the Maldacena consistency relation. And based on that, I will show you how we can prove that the bispectrum vanishes in the most simple cases of single field source inflation. Okay. As people know, the scale-dependent halo bias is sensitive to the primordial non-Gaussianity. There are some people working on this subject. This parameter, FNL local, comes from the initial condition of the universe. For initial conditions, I mean inflation. Here is the $1 million question and the true motivation of this work. What kind of inflationary models can produce a detectable amount of local non-Gaussianity? The answer is easy, I don't know. but let's try to elucidate what kind of models cannot produce it. By the way, this is the only slide which is related to something of large-scale structure. Okay, let's start with the ingredients. So inflations emerged as a solution for many problems of the early 80s, I think, and also to give us the initial conditions for the structure formation of the universe. Physically, inflation is a period in which the common Hubble radius decreases. We can work out a little bit this expression, and this is equivalent to this one. So inflation is the period in which this parameter epsilon is smaller than 1. There is also another parameter, eta, which tells about the duration of this expansion. So in the standard Big Bang theory picture, we know that in the early universe there is only radiation and matter. And that content is unable to produce this period of expansion, if you want. So we need to add another ingredient, and the most simple choice is to choose a scalar field minimally coupled to gravity. So if we vary the action with respect to the scalar field, we obtain the Klein-Gordon, the usual Klein-Gordon equation. And if we use these two approximations, which is known as the slow roll approximation, we end up with this reduced Klein-Gordon equations. So basically, we are neglecting the second time derivatives. What is important about this equation is it has an attractor solution, which means the solution is independent of the initial conditions. But if you want, in the phase space, all the trajectories goes to the same point, always, independent of the initial conditions. This is an important feature of this model, the slower. Okay, this is the background part. Here the field only depends on time. But also we need to consider the perturbations around this field, which depends on time and on space. To deal with perturbations, it's useful to work with the ADM formalism. In this way, we can turn off the perturbation of the scalar field and move that to the metric tensor, or one of the scalar degrees of freedom of the metric tensor, and choose a particular gauge. This is the comoving gauge, and this is called the comoving curvature perturbation. So once we have this, it is useful to write the action in terms of the ADM variables. I always forget this. This is the shift. This is the lapse function. Maybe not. But what is important is that we need to write the action in terms of these variables. We vary the action with respect to them. We solve their equations, which is these are the solutions, and replace them again in the action. And at the end of the day, we have found an action for the curvature perturbations. The perturbations are the most important thing in this way because they tell us about the observables in the sky, such as correlation function, the power spectrum, the Pi spectrum, and so on. Okay, this is the behavior of the perturbation in this framework of slow roll inflation. When the perturbations are outside the horizon, they freeze. This is demanded by the adiabaticity condition of the CMB. And the perturbations inside the horizon oscillate freely. When the long wavelength perturbations re-enter on the horizon can oscillate also. But when they are outside, they remain constant. That's for adiabaticity. Okay. So let's talk about the observables, which are given by the correlation functions. In particular, the 2-point correlation functions give us the power spectrum, which is well constrained by this parameters, which is the scalar amplitude, the spectral index, and they are measured at some particular pivot scale, K0. Another important quantity, which is really important for this work, is the bispectrum and the 3-point correlation function, which tell us about the existence or the non-existence of non-Gaussianities. We can take the limit in this expression of one of the momenta of the perturbation goes to 0. And in this way we can define the parameter FNL local. Here we have the prediction of single field slope inflation for the power spectrum. What is the prediction for the bispectrum in the squeeze limit from single field inflation? The answer was given by Maldacena, and he found this beautiful relation. This is known as the consistency relation, which indicates that the bispectrum is related to the power spectrum through the spectral index. This expression was obtained from the cubic order action for the curvature perturbations, which is a little bit difficult. But what is important, this relation indicates us how two short modes, K1 and K2, are modulated by a long mode. This relation is really important for inflation because it's a crucial test for all single field attractor models of inflation, because we can quantify this relation in the parameter FNL, which is related to the spectral index, and this number NS is well constrained nowadays. And this is something like 0.02. This is the actual value given by Planck. Okay. This is the last ingredient that I need. This is another way to obtain the Maldacena's consistency relation based on the observation that the relation is obtained from the modulation of a long mode to short mode. So first we start with the metric, the perturbed metric. Then we note that the metric is invariant under this chain of coordinates and fields. Here the space coordinate is transformed like this, and the spatial coordinate transform, not transform. And the perturbation transform in this way. Then we can always split the curvature perturbations in their two contributions, the short and long wavelength part. Once we did this, we know that the short part is related to the zeta prime part, which is solution of the full equation of motion. So we are interested in compute the 2-point correlation function for this guy. And we can compute through this relation. The strategy here is expand this relation and then move to Fourier space. And we have this. And finally, we correlate this expression with a long mode. And we found this expression. That was found by Criminali and Sarah. So we know that the squeeze limit appears at the limit when K3 goes to 0, in this way. So we have recovered the standard Maldacena result in a more clear way. Okay. Now I have all the ingredients. I will talk about what we did. First, I want to introduce these kind of models of inflation, which are known ultra slow roll inflation. Basically, the inflationary potential is a constant. the model is interesting because there are some people working on this which use this model as a mechanism to generate primordial black holes. The model has some other interesting features, such as the curvature perturbation in this kind of model, satisfy the adiabaticity condition, but not necessarily freezes outside the horizon. We can have in this case a super horizon evolution of the modes. This is really, really important in this class of models. What else? Conversely, from slow roll inflation, this model has non-attractor solutions, which means that the background depends strongly on the initial conditions. The model also has almost a scale invariant, but in the way in which it's presented, has a big problem. The model never ends. Inflation never ends in this kind of model. So there must be at least a transition regime between ultra slow roll inflation and slow roll inflation. There are some people working on this subject. But why the model is really interesting, at least for me? Because the model produces a big non-Gaussianity and breaks the standard Maldacena consistency relation. So if one computes the bispectrum for this model, a la Maldacena, what we found is this, which is a explicit violation of the Maldacena result. So there are two options. The consistency relation is wrong, or is missing something. Something which comes from the non-attractor or ultra-slow roll part of inflation. So let's try to fix this. For that, I will use the receive used by Cremineni and Saldarella. And I will start with the metric. And this time, we know that the metric is invariant under the following chain of coordinates and fields. Now I'm changing the time coordinate in this way. Here, T star is some reference times. It could be the horizon crossing moment, if you want. And theta tau is the super horizon mode for ultra slow roll inflation. Again, we split the full mode in distributions, and we found that the short mode is related to the full mode in this way. Same as before, we expand we compute the tubal function and expand both in time and space, and we found this. Then we correlate with a long mode. What we found is this. So if the super horizon mode freeze, we end up with the Maldacena standard attractor result, so namely this part. But if the mode grows on the super horizon scale fast enough for this term becomes subdominant, we end up with this expression, which is the missing part of the consistency relation, which the non-attractor part. So if we apply this consistency relation to the ultra-slow roll models of inflation, in which the curvature perturbation depends on time in this way, the power spectrum is quadratic in the curvature perturbations. So we have this dependence we put here, and we recover the result found by Chen and company. So this is a good consistency check that the relation is good. What is interesting for this derivation also is that in the previous case I used that the epsilon parameter is equal to 0. But this is not a necessary condition. Okay, if I start with the same metric and this chain of coordinates of fields, I found this relation. So the metric is not invariant unless this guy is equal to 0, or if we neglect epsilon. In the previous case, I have neglected epsilon. But if has this dependence, I also recover the result. So what we say is the transformation of coordinates is an exact symmetry of the metric for the case of ultra-slow roll inflation. Okay, something interesting is that the previous result, the standard consistency relation of Maldacena and this one predicts the bias spectrum through a coordinate choose. And that sounds a little tricky, sounds like a gauge artifact. So we will deal with that in this section. So we can always construct a set of coordinates in which an observer can only measure the physics in their local environment. This set of coordinates in the context of cosmology is called the conformal Fermi coordinate frame. So it takes account that the super horizon modes are invisible for an inertial observer. So if we compute the coordinate transformation in this set of coordinates, they transform like this. For the case of slow roll, ultra slow roll inflation. This is a linear order in the coordinates. So here the quantities with a bar are the quantities in the Fermi frame, which are the gauge invariant, if you want, quantities, or are the observer quantities. So we are interested in compute the correlation function in this set of coordinates. If we compute the triple function, what we found is this, which can also be read in this way, that the observable bias spectrum is given by the comoving bias spectrum plus a correction. The comoving bias spectrum is given by the symmetries that we found. And what is interesting is that the correction is always the opposite of this. So at the end of the day, we found that the observable bias spectrum always vanishes for the case of slow roll and ultra slow roll inflation. This was not for the case of slow roll inflation by Deskey, but now we can generalize the result for the case of ultra slow roll inflation. So what we say is the observable local FNL is equal to 0 up to corrections of higher order, which are negligible. All this has the origin in the symmetries of the system. So the symmetries that we use to derive the consistency relation has the opposite sign of the transformation of Fermi coordinates. So the statement is that the modulation effect of the long mode is cancelled by the rescaling coordinates. The result is independent of the behavior of the background. Another interesting thing is that if we expand the Fermi coordinates at higher order, what we found is something known, which is a conformal transformation, special conformal transformation, which the people know this kind of transformation is also a symmetry of inflation. But we can continue expanding this expression, and we find another terms, and probably they are also symmetry of the background. This is a work in progress. Okay, to finish, these are the conclusions. We have generalized the standard consistency relation for models which exhibit a super horizon evolution of the modes. We have shown that the biospectrum in both cases vanishes always. So the most important conclusion is this one. If tomorrow we measure an FNL local different from zero, from where does it come from? What kind of inflationary can produce that? Multi-field models, non-bunch Debye, vacuum models, models with non-canonical term, etc. Thanks for your attention. Thanks.
Questions?
Yeah, so do you know what happens in these models after reheating? Because, for example, the vanishing of the bispectrum is during inflation for a local observer, and I don't know how inflation ends in these models. So do you have any idea of?
No, the relation is valid only during inflation. Okay. There are some people studying what happens in the before inflation ends. So sorry, after inflation ends, and for two regimes in ultra slow roll, smooth regimes and a non-smooth regime. For one of the cases, the cancellation persists, and in another case, none persists. But it's not there is not a constancy in the answer. I don't know.
Yeah, just a comment. For the last point you raised, there is a paper by Justin Curry and others that explore like the most general transformations you can do on the metric. So maybe you can look at that to see. They explore to any order in X when you expand. So
okay.
Maybe you can take a look at that.
Thank you.
More questions?
So maybe I didn't quite understand. Usually we have to make sure that these modes that we are using to rescale the coordinates are adiabatic modes. So is this also the case in this ultra slow roll, even though they depend on time?
Sorry?
Even though this in the ultra slow roll inflation, these super horizon modes can still depend on time.
Yes, depend on time, but
they are adiabatic.
They are adiabatic.
Okay.
So thank you again. Now we have a coffee break.
For dinner. So for dinner, dinner's at 8 at this place. And Antonino will be at the Universidad flat at 7:30. I will leave from here at 7:20. So you meet here if you want to leave from here.
So when you say here,
Here at the auditorium. That's the best place to eat.
I think it's really fair to Antonino to
Yeah, okay.
Excuse me. Oops, sorry.
Quítate primero el zapato. Sí, ya hablé de la generalización de X. Ya está hecha. Es la disolución de Curry.